for the next couple of weeks, we're going to switch gears and talk about mostly unsupervised learning, or I guess not strictly unsupervised, but things related to unsupervised learning, learning with missing values, partial supervision, things like that. And so today, we're going to start with the most basic aspects of unsupervised learning, which are clustering and dimensionality reduction. Okay. And you can think of dimensionality reduction as a form of matrix factorization. This will become clearer throughout this lecture and the lecture on Thursday. So what is clustering? Clustering is the process of grouping data points into clusters. Okay. I don't know why I wrote that. In retrospect, it's kind of obvious. Anyway, so the goal is for these clusters to have high intra-cluster similarity and low inter-cluster similarity. So things that are within the same cluster should be more similar to each other than things between clusters. So here's just a very simple example. It's a very toy example. Can anyone tell me how many clusters are in this example? Great. 3 clusters. All right, color-coded them for your benefit. And so the idea of clustering is, given just data points, so think of these as just x's, and in this particular case, 2-dimensional x's. Find the number of clusters, cluster the data points into these clusters, so that within each cluster, the similarity of points within the cluster are more similar than between clusters. And here, similarity is measured using the using distance within the raw feature representation. So these are 2-dimensional x's. Distance is the measure of similarity. You could imagine, in general, more abstract notions of similarity. It doesn't need to be distance within some feature representation, but in this, for now, we could just think of it that way. Although everything that we talk about generalizes to more abstract similarity measures as well. Okay, so clustering, at least this sort of simplest form of clustering, is an instance of unsupervised learning. We looked at unsupervised learning briefly when we talked about naive Bayes and HMMs. And so the basic idea of unsupervised learning is, you only have unlabeled data, a training set of unlabeled data, no labels, and so just the input features. And the goal of unsupervised learning is to find some notion of hidden structure or patterns in the data, right? So finding the clustering is one example. In the previous couple of weeks, we looked at HMMs and naive Bayes, which is saying, given a certain structure of how data is generated, find a generative model of this data. That's also, you can also think of this as a hidden structure or pattern in the data. So why is clustering useful? Well, you can think of clustering like many of these unsupervised learning algorithms. You can think of it as a summary of the data, right? We can actually just look at the cluster centers as a summary. So for example, if we've looked at that previous data set, and we noticed that there were 3 clusters, then we can actually very succinctly summarize that data set just using 3 cluster centers, right? Or we can also just select a few data points per cluster. So rather than having to look at the entire data set or the entire raw feature representation, we can just look at just a small slice of that data or a small viewpoint of that data and get a sense of what the data is trying to tell us. And that's the goal of these sort of models that make these simplified assumptions that allows us to summarize the data in a much more compact way than the raw representation. So here's just one example pulled from this paper. This was done for a few years ago, so this will probably change if we do it now, but if one did an image search for the word Pluto and clustered the images based on some notion of image similarity, then you can think of each row as a cluster of images based on some notion of image similarity. The simplest one is pixel by pixel distance, treating each pixel as sort of a feature value. And so you see the top one is, I actually don't know what exactly that refers to. This is an old furniture brand, The Planet, some really old movie, put up the cartoon dog, and so on and so forth. Right? So these are clusterings of images that are returned when you do an image search for the word Pluto. So as you can see, at least in this example, which was admittedly a little bit cherry-picked, the clusters make sense, right?
So you said that the distance here was what? So
I don't actually know exactly what they did, or I don't remember exactly what they did. I would imagine the simplest thing you can do is pixel by pixel distances. Yeah, so you would scale these images to a common dimension, and then treat each pixel as a feature value. They may have done something a little bit more sophisticated. But so long as you define a distance function or a similarity function, you can do clustering. Another reason why clustering might be useful is that it gives you a compact pre-processing of data before you use it for supervised training, right? If we can somehow reduce the dimensionality of data into just the dimensionality of the number of clusters, then we could take something that's really high dimensional, like maybe 1,000 dimensional, if there's only 5 clusters of data points, we could reduce it down to a 5-dimensional representation, right? Assuming, of course, that that's the clustering is the only data we would need in order to do supervised learning, and this would be a way of sort of doing compact pre-processing. Yeah?
So you could use a membership in a cluster in like a 5-feature vector?
That's right. Yep, that's exactly how you would do it. So this is the demonstration of the most commonly used clustering algorithm called K-means. It is a centroid-based clustering algorithm, and I'm just going to walk you through how it works. First, we initialize. We posit that there's 3 clusters, so K equals 3. So K is the number of clusters. We posit that there's 3 clusters. We randomly initialize the data points with every data point with a random assignment of cluster identity. So every data point is randomly assigned one of the 3 cluster values. And here the cluster IDs are color-coded. What the K-means algorithm then does is it estimates the cluster centers. So each of these represents the cluster centers, which is the average of, this one's the average location of all the black dots, this one's the average location of all the blue dots, this one's the average location of all the red dots. Okay. Given the cluster centers, the K-means algorithm updates the memberships. So every point is now assigned a membership of the cluster whose cluster center is closest to. Right, so we started with random initialization, we estimate some cluster centers, and now we're reassigning the clusters to the cluster IDs of the individual data points to be the cluster center it's closest to. And then from this we estimate better cluster centers, right? So now this is now the average of the black dots, this is the average of the blue dots, the average of the red dots. And then from this new updated cluster centers, we compute updated cluster memberships, we compute updated cluster centers, updated memberships, updated centers, updated memberships, updated centers, updated memberships, until we converge. And at this point, we terminate. So at this point, the model will not do anything new, right? Given these cluster centers, it will not change the cluster memberships. And this is where the K-means algorithm terminates. So we can think of the K-means objective. By the way, can anyone tell me what general class of algorithms this is? You've seen it before, the general class. Yep.
Isn't it basically like a generalized perceptron type thing? Or is it maybe not the class?
No, so I think unsupervised learning.
In tracking, you said that if you don't have the tags, you do something similar.
That's right. So this is an instance of EM, expectation maximization. So I'll make that clear in a few slides. Right? Just like in HMMs, where if you don't have the labels of your model required by your model to fully specify the model, you do this alternating optimization where you estimate the model parameters, predict the best memberships of tags tags, and then you rinse and repeat. So I'll make that clear in a few slides.
How do you know it converges?
What's that?
How do you know it stops?
How do you know that it stops?
In
Well,
a reasonable way.
so you know that you always make progress at every iteration because so one way to think about it is look at the objective function. The objective function is as follows. The parameters of a K-means clustering algorithm, the model that you learn, is basically the cluster centers, right? Given the cluster centers, the model is fully specified, right? Because the cluster that each data point belongs to is the cluster center it's closest to, right? So the goal is to, given this training set, learn a partitioning of the training set into clusters, as well as the parameters of the model, which is the cluster center, which are the cluster centers, that's such that you minimize the square distance between the data point and its cluster center, right? So now we sum over all cluster IDs, sum over all data points in that cluster, and then we compute the square distance between that data point and its cluster center. And the K-means objective is to find the partitioning of the cluster centers parameterization that minimizes the objective function. So this is equivalent to minimizing the unnormalized variance of each cluster. So let's talk about the EM algorithm, and then we can talk about why it converges. So the EM algorithm for K-means, which is exactly what I just described before, is the E step, you estimate the cluster membership of every data point. And then given the cluster, so you alternate between optimizing over this guy and optimizing over this guy. So you estimate the cluster membership of each data point, just like you in HMMs, you estimate the marginal distributions of the tag sequences. And then the M step is given the cluster memberships, you estimate the model parameters, which are C. So given the marginal distribution, like in HMMs, given the marginal distribution over the tags, you can estimate the new probability tables. Right? So it's the exact same setup where you have some estimation that your model gives, plus parameters of your model, and then you alternate between estimating the model and fitting the parameters of your model until you converge. Why does this converge? I think I showed this in the next couple of slides. So in the E step, just to reiterate, so for every data point in our training set, given the current cluster centered model parameters, we assign X to the cluster with of which it has smallest distance to the cluster center. Right. In the M step, when you fix the cluster memberships, we estimate the new models of our parameter. Right. So why is this guaranteed to converge? Well, I can prove that at every iteration, I'm minimizing this objective function, right? And I can also prove that this objective is bounded from below, right? So, and I can furthermore prove that you can furthermore prove for any finite data set that there's a minimum step size. For any finite data set, there's a minimum step size of progress you can make if you are making progress, right? It depends on the granularity of the data points between distances. Therefore, you can prove that it converges.
But it may converge to a local minimum, right?
That's right, it may converge to a local minimum. That's right, and in general, HMMs also converge to a local minimum. In general, EM algorithms will not converge to the global minimum, global optimum. So what people do is they do random restarts a bunch of times, and then they pick the best solution that has the lowest objective score. And keep in mind that I haven't even told you how to choose the number of cluster centers, K. That's typically done via validation. So when I talked about probabilistic models at the end of the naive Bayes lecture, I mentioned this Gaussian mixture model where we have a bunch of data points, and every data point belongs to a bunch of clusters, and every cluster is specified as or quote unquote, maybe not clusters, but there are sort of K Gaussian distributions, and then every data point is sampled from a mixture of these Gaussian distributions. So here's a mixture of 3 Gaussian distributions on a one-dimensional feature representation, and this is the distribution of data we get from this one-dimensional Gaussian distribution. You can think of Gaussian mixture models as a probabilistic version of K-means, where instead of a hard clustering for each data point into one of the cluster centers, we have a probabilistic cluster, right? So this is just one formulation. It's not the only formulation we can use. It's just one. It's the simplest one, where the probability that a data point, given the parameters in the model, which are the cluster members, which is our cluster centers, the probability that a data point belongs to a certain cluster is proportional to this ratio. Right? And the sharpness of this distribution increases so how peaky it is, increases as sigma decreases. And in the limit as sigma goes to 0, this exactly becomes K-mean, it exactly becomes hard cluster. And so for Gaussian mixture models, you would do something very similar, right? You'd also do this EM, where in the E step, instead of doing a hard assignment, right, like in K-means, we would do a soft assignment where we estimate the probability, given our current model, of x belonging to each of the clusters. And then in the M step, given these estimated probabilities, we would pick the cluster memberships, cluster centers, the model parameters that maximizes the probability of the data. Just like in HMOs. Like the EM algorithm is a very generic algorithm where if you assume that there's these hidden model parameters that summarize your data, then you alternate between estimating probabilities and maximizing setting model parameters to maximize the likelihood of your model given the estimated probabilities. Any questions on that?
Why we are summing over k in the objective function? That will be 1, I think.
Summing over
K, yes, because we have capital K groups and the summing over k will be 1.
Right, let me think about this. I may have made a mistake on this. Let me think. You are correct. I will fix this slide. Yeah.
Is it the sum of the product or split? Because you want the joint probability of the cluster, right? So you multiply product first and add over each cluster. For each cluster, you multiply the probabilities together. And you sum over all the clusters, right? So.
I don't want to think in real time because I'll probably say something that's also wrong.
Okay.
But there is a mistake on this slide. I'll fix it. Just to recap on k-means, it's a centroid-based clustering algorithm that defines clusters using a notion of centrality, and then all clusters in the cluster must be close to each other by definition of how you define centrality, solve using EMs, also probabilistic variance. And this is useful when the centrality assumption is a good assumption for defining clusters. Of course, like any model, this is bad when the centrality assumption is a bad assumption to be using for your data set. So here is a thought experiment. I gave you a new set of data points. Now this is of course contrived, but I picked it especially to illustrate a point. And now I've given you two different clusterings, right? One is based on the black circles with 7 clusters, and one is based on the orange circles with 2 clusters. Now the question now, of course, is which one of these two is a better cluster? Right? On the one hand, in some sense, the black one is better in that it's a better summary of the data, but of course it has 7 parameters as opposed to 2. And maybe these 7 parameters are fictitious, right? Maybe because of the small data set size, there really are these 2 clusters, right? Or maybe the idea of centrality-based clustering is not a good modeling assumption for this type of data because there isn't really much centrality going on, right? It's like hierarchies of little clumps of stuff, right? It's not quite the same notion of centrality as we talked about with k-means. And the way people deal with these types of data distributions is instead of using centrality-based clustering, they use linkage-based clustering, also known as hierarchical clustering. Although hierarchical clustering is a bit ambiguous because it can also be applied in other ways, but linkage-based clustering is definitely always hierarchical. Right. So this particular one that I'll talk about is agglomerative clustering. Here's how it works. In agglomerative clustering, it is basically you start by assigning, you look at all pairs of data points. This is the naive version. You could do something much more efficient, of course. But the naive version is you look at all pairs of data points. And you find the pair that's closest, and I link them together. Now I treat them as a supernode, one data point, right? And then I find the next closest pair that's unlinked, and I link them together. And this process continues.
So when you link 2 data points, you consider it as a single data point with coordinate the center of the midpoint of those?
It's actually it'll be considered, so there's different ways you can do it. One way is to consider this as a point that has surface area or volume. So the distance is actually the closest distance.
I see.
Yeah. So not a point mass, but something that has surface area or volume, right? Some people use the center. Like there's no strict way to do it, but I think the one you read about first when you look at Wikipedia or a textbook would choose the one that's closest. So the distance between these two groups is this point and this point. And so at this point, we decided these 2 points are the closest, right? Out of the remaining unlinked data points. So now we have a hierarchy. So we say we're going to link this point with this pair of points. And this process just continues until we've linked everything. So now we have a spanning tree over the data points. And the structure and the order with which we added the spanning tree determines what the root is. And then the leaf nodes are the sort of the agglomerative clustering. So we sort of build this clustering from the ground up. So for those of you who are, who've taken, is it CS 21? Is that algorithms? 38, CS 38. You'll notice, you should notice that this is equivalent to finding a minimum spanning tree algorithmically with a little bit of add-on that you keep track of, and that is equivalent to Kruskal's algorithm for finding a minimum spanning tree. The order that the edges are added defines the cluster hierarchy, so that's what you have to keep track of. Otherwise, it's exactly the same as Kruskal's algorithm. And it's also equivalent to finding a binary tree partitioning with progressive similar partition distances. So this is a linkage-based version, right? This is a linkage-based, so there's no sort of single notion of centrality. It's sort of a hierarchical notion of linkages. Right? There's really no notion of global notion of centrality in this type of clustering algorithm.
So I don't understand, what is the final type of cluster? You fix the number of clusters and you stop when you have that many connected components?
So actually this is a agglomerative clustering defines many clusterings, right? Any cut, so if I were to draw this out as a binary tree, right? Any cut of that binary tree defines a cluster.
So which one is like the best one?
Depends on your use case. So this is often used in, for example, in biological studies where they analyze the interaction between different transcription factors or things like that. And there's different strengths of interactions, right? You want to see, are there clusters of genes that behave, let's say, in a regulatory pathway? And what people do in those types of domains is they do something like some sort of agglomerative clustering, right? And then they decide what level to cut it at from just visualizing the hierarchy, based on the strength of the connections. So this is more like the data mining part of the course where there is no sort of hard and fast answer. A lot of this is very much based on how you're trying, what insight you're trying to glean from the data. So, and certainly this type of approach is very popular, for example, in the biological sciences. Okay, so just to recap on clustering, it's perhaps the quintessential unsupervised learning technique. It posits some sort of clustering structure over the input features, and then it finds a clustering model that obeys this, whatever structure you posit, that best fits the data, right? There are two basically high-level approaches. There's centroid-based approaches, which posits that clusters should contain data points that are clumped together, and these can be solved using k-means. And then there's linkage-based structure, where it posits that these data points can be sort of clustered hierarchically, and one approach is agglomerative clustering. There's also top-down clustering rather than agglomerative is bottom-up. You can also do top-down. These methods work great when the clustering assumption, whatever one you impose, is good. And of course, they work not so well when the clustering assumption is not so good. Yeah?
Like, is the assumption for the second one the same as the first one, or what is it?
Which one?
For the linkage-based one, how's the assumption?
Well, if you try to choose a K, right? If you try to choose a K, right? A single K that that clusters this into, like, let's say 3 centroids, right? It's not obvious what that K should be, because there's a lot of sort of recursive, if you will, a centroid behavior. And that's not the right way. That's a little imprecise, but one way to think about it is, like, here's sort of a group of data points, so maybe K equals 3, right? But on the other hand, here's smaller groups of data points, so maybe K equals 7, right? And we don't know. And there's a lot of, and perhaps we see this sort of more recursive structure in the centrality, in these centrality measures. And one way to get around this is to do agglomerative clustering, which posits that we have this hierarchy of clusterings, and whichever cut you want to use that makes sense for your analysis is the one you should use. But it recovers all of them simultaneously. Now that's a little bit imprecise because it doesn't always have to be centrality based. Like, it's just due to the fact this is a 2-dimensional example. In a high-dimensional example is what I just said may not apply. But there's an assumption that you could find these hierarchies of clusters. Yeah.
How stable are these algorithms? Like, if I added a new point that happens to be close, could I totally screw up the hierarchy, or is it usually?
For agglomerative clustering, it can be unstable, right? If I added a point here, it can really screw things up.
Yeah,
right?
that's what I was thinking.
Yeah. So it can be unstable. It's relatively stable to jittering of existing points.
Yeah, because it's just.
Yeah, so if you have measurement error, so like in biology, right, the number of genes is fixed,
Yeah.
but your measurements on them may be noisy. So it's relatively stable to measurement error of a fixed set of points. Okay, so what are some limitations of clustering? Well, okay, so can someone cluster this data set? Clearly there's structure in this data set, right? I mean, we can all see it. It's sort of tilted along this axis, but can anyone cluster? Give bonus points anyone who can do it convincingly.
It sort of looks like 2 overlapping bubbles, but
Sort of, but not really, right? For 2 overlapping ovals, there should not. You would see two places of maximum width, rather than it's actually just a single oval.
And it kind of looks like it's like a torus that's been shifted in 3D. So if you can imagine being rotated and having like a hole under or something like that from this perspective.
I see. So now you're going to cheat and assume that there's a 3rd dimension that we haven't seen. Okay, that's fair, but that's not the answer I was looking for. In fact, there doesn't exist a good answer. So I promised to give out 3 points because I knew no one was going to be able to answer it. So the reason why this type of data set is not good for clustering is because it's clustering posits that there's some notion of grouping data points together that gives you a summary of the data. But in many cases, you don't want to actually group data points together. You want to recover dimensions of the data, right? Somehow this dimension, right, of the raw data, this dimension is semantically meaningful, right? And then this dimension is the other semantically meaningful dimension, but this is the dominant semantically meaningful dimension. Right? This is the direction of maximum correlation. And that is what principal component analysis seeks to find. It's also an unsupervised learning algorithm. Well, I mean, it predates machine learning by a long time, but machine learning has unabashedly adopted it as an unsupervised learning algorithm. So here's how it works. So summarizing data. So the idea of principal component analysis is instead of summarizing data using a small number of cluster centers, we're going to summarize data using a smaller number of features directly. And that means, so for example, if I wanted to summarize this data set using a single feature, right, I would ask, where does any data point project along this line, right? If I had to summarize this data set using just a single feature, that's the single feature I would use, because it would preserve most of the variability of this data set. And I'll make this formal in the next few slides. So PCA, so clustering, clusters via, this is using k-means as an example, via cluster membership. So if I were to use that to summarize the data, it's the cluster membership IDs. That's what I use to summarize the data. In PCA, I summarize via orthogonal projections. So I define a new feature representation that is a rotation and a projection of the original feature representation. Right? So if this is the data and the original feature representation is the horizontal axis and the vertical axis, I want a new feature representation that defines a feature that's how far this data point, each data point projects along this direction or this rotated axis, and how much each data point projects along this rotated axis. And hooray. Right, so this would be the new feature representation, right? And I could just, there's no reason why I can't rotate the data set, the raw features, so that I have a new feature representation, so that now the feature 1 corresponds to how much each data point projects along that diagonal line. Now I've just rotated it. So now this is my new feature 1, and this is my new feature 2. And if I had to just choose one feature, I would just choose feature 1 because it's the single feature that captures most of the variability of the data points. So a little bit of matrix linear algebra. So let U be what's called an orthogonal matrix. And a matrix, and U is going to be a square matrix in this case, or actually it doesn't use square. So U is orthogonal. If UU transpose and U transpose U gives you the identity matrix. What that means is that for any column, U transpose U equals 1. Now for any two columns that are different from each other, different columns of U, U transpose U and U prime, U transpose U prime equals 0. So every column is a unit vector, and every column is perpendicular to every other column. That's what defines a orthogonal matrix. Orthogonal matrix is any matrix where its columns obey these properties. If U is full rank, so it's a square matrix, then U is a rotation matrix, and U transpose is the inverse rotation, because U transpose is also U inverse. Right. So one can use U to define a new x prime that is basically a rotation of the original data point. So now this is x prime. So now the coordinates of x prime correspond to these dimensions of orthogonal high variability. And PCA is a method that finds a specific U. So properties of an orthogonal matrix, it's norm preserving. If it's full rank, it's norm preserving. So the inner product of x prime transpose x prime is equal to this, is equal to this, is an identity, so it equals this. Right? So therefore it preserves the total variance of the data points.